And welcome to this channel, and in this video I'll be discussing with you the Bernoulli's principle. Okay, so let's get started and understand NCRT line by line. Before that, I'll give you a quick summary or the quick crux of what the Bernoulli's principle is about. Okay, so basically Bernoulli's principle states that the total energy, it is based on conservation of energy. Okay, so what it says that the pressure energy, suppose there is a pipe, okay, and the fluid is flowing through this pipe. Well, fluid has to be incompressible, it has to be streamlined flow, the flow has to be laminar or streamlined. Okay, in that case you can see the pipe is at different height here. Okay, so obviously the potential area, these 2 points or this two cross section area will be different, and also there will be the kinetic energy. Suppose the velocity is v1 here and v2 here, the velocity will be different. So velocity will be different, potential will be different, and the pressure, let's assume the pressure is also different in those two region or the area. Okay, so what Bernoulli principle state that the pressure energy, okay, plus the kinetic energy plus the potential energy, okay, sum of these three will be constant. Okay, so what will happen, the pressure energy may change, yes it will change. So there will be change in kinetic energy, there will be change in potential energy, but the sum of these three will be a constant, and which follows the law of conservation of energy, total energy will be conserved. Okay, so let's understand this in more detail through ncert. Fluid flow is a complex phenomenon, but we can obtain some useful properties for steady or streamlined flows using the conservation of energy. Okay, so consider a fluid moving in a pipe of varying cross sectional area. Okay, just as I told you, like we have seen that pipe, and this is the pipe we are talking about. Okay, the varying cross section area, the area is a1 at this point and a2 at this point. Now further, let's go. Let the pipe be at varying height as shown. We now suppose that an incompressible fluid is flowing through the pipe in a steady flow. Okay, so the fluid should be incompressible. So there are some assumption that we'll talk about later part of that there are some certain assumption that we have taken for this to be to prove this. Okay, the fluid has to be incompressible, it cannot be compressed. Okay, it's flowing through the pipe in a steady flow. Its velocity must change as a consequence of equation of continuity. You have seen equation of continuity, it states that the, okay, because the area of the pipe is varying, the area is smaller here, larger here, and it says that the principle of continuity, a1 v1 is equal to a2 v2, means where the area will be less, the velocity will be more, and where the area is more, the velocity will be less. Okay, let's go further. And now, yes, a force is required to produce this acceleration. Okay, the velocity is changing, so obviously there is acceleration. Okay, change in velocity, and there is a acceleration, so there must be a force acting. Okay, which is caused by the fluid surrounding it. The pressure must be different region. Okay, so the, okay, the in this region, okay, there was a fluid, and this has moved to this part. This much fluid will move to this part, and obviously it has accelerated. Okay, its velocity has changed, so certain force has been acted. It has been acted by the surrounding fluid. Okay, the fluid surrounding it has exerted that force that changes its pressure, okay, and also its velocity. Okay, so now, uh, which is caused by the, yes, must be different reason. But Bernoulli's equation is a general expression that relates the pressure differences between 2 points in a pipe to both velocity changes. Okay, obviously, as I told you, what it relates, pressure difference to velocity changes, and potential energy, potential change. Okay, now consider the flow at two regions BC and D. The do region you can see clearly in the diagram. BC region and D region, 1 and 2 region they have mentioned it. Okay, now in an infinitesimal time interval delta t, this fluid would have moved. Okay, we have taken a very small time interval, very small delta t time. Okay, suppose v1 is the speed at b and v2 at d. Then fluid initially at b has moved a distance v1 delta t to c. Okay, so okay, the velocity is here, it's v1 at this point, at b point. Okay, and it has moved in delta t time. What is distance? Distance is velocity time, velocity multiplied by time. Okay, so it has moved in delta t time, it has moved this region. Okay, we are v1 delta t. Okay, now the volume will be what, how much volume it has swept in this delta t time. So you know volume is area times the length. So a1 is the area of cross section here, this part. Okay, and for as you have taken delta t very small, so the area will, the region, this region, the area will not increase significantly, it will increase only infinitesimally. Okay, here will not much difference, so we can multiply delta a by this length, that is v1 delta. This is the volume of the water, uh, the liquid of this cross sectional area in delta t time. Okay, now further, let's go further. Okay, then in the same time interval, yeah, okay, let's see. Yes. This is what I have told you. V1 is the speed at B and V2 is at D. Then fluid initially at BS moved a distance delta T to C, and V1 delta T is small to assume constant cross section along BC. We have discussed this. In the same time interval delta T, the fluid initially at B, D moves to delta E, distance equal to delta V do delta T. Okay, I told you all this also. In delta T, the velocity will here in this region V2 velocity is there. So V2 time delta T, the volume will be, how much volume will be swept? A2 V2 delta T. Okay, for the same time instant delta T, I'm assuming the fluid has this much volume has been moved. Okay, and in this much volume has been moved in the same time interval. Okay, now wait for a second. Yes, yes, so what, where we were, pressure P1 and P2 acts as shown on the plane faces area A1 and A2 binding the two regions. Okay, there are pressure, they have shown the pressure. Yes, the pressure P1 and there is P2 pressure. Okay, and now yes, so the work done on the fluid at left hand is W1. So how much will be the work done? We know the volume is there. Okay, as we have seen, the volume can be determined like this, and also you know volume work done is force into displacement. How much is the force? Force is pressure multiplied by area, and the distance is v1 delta t. This was the work done. Okay, and now a1 v1 delta t is delta v. So work done on the left region on the fluid is v1 delta v. Since the same volume delta v passes through both region, okay, has the volume has to be same. Okay, so if from equation of continuity, as we have seen that the same mass flows. Okay, suppose m mass or v volume enter a pipe at particular time, then in the same time interval, same mass or same volume will be exit from the other end of the pipe. Okay, so this, the volume has to be same. The work done by the fluid at the other end is w2. Okay, what is the work done by the fluid at the other end? This work. Okay, here work has been done on the fluid. Okay, and the work done on the fluid or this end, or the work done by the fluid. Okay, how much force it is exerting on the neighboring pipe. Here the force was exerted on it to accelerate. Here it will exert certain force on the neighboring fluid. How much work it will be exerting? Again, force times the displacement, and force is p2 a2 in that case. Okay, p2 a2 and v2 delta t. Okay, similar, it is same like above. To p2 delta v is the work done, okay, on the fluid, by the fluid, and on the fluid it will be negative. Okay, it will be opposite, because here work is done by the fluid. So what, how much work is done on the fluid will be negative of P2 delta. Okay, so positive means that energy is being used up. Okay, and negative means it will be negative. What will the negative? Negative will be work is. Okay, let's understand this other example. Like, okay, you see, if I lift a box, I'll take another example. Okay, a box above height. How much work I have done? I suppose I have done 10 work. Because why 10 plus 10? Because the force is in this direction, my force was in direction and displacing this direction, the work is positive. Okay, energy is being used up. Okay, but uh, how much work earth has done? So earth has done the, in magnitude has done same work, but there will be a negative sign. Okay, because you know the force was, earth's force was in this direction, gravitational force, the but it has moved opposite direction, so in that case cos 180 is minus. Okay, so this is negative work. Okay, so that's why the work done by me, external force, was positive, and work done by the earth is negative. Okay, and this energy is stored for earth, energy will be stored, potential will be stored, but for me I have spent some energy. Similarly here, so work done by the fluid, fluid has some expense of energy. Okay, so this will be positive work, and the work done on the fluid will be negative. Okay, uh, so now the total work done will be, because work is scalar quantity, we can add them. Okay, we w1 and w2, what how much is the external work we are talking about? No, w1 was the external work, w2 is also the external work, so it will be negative. Okay, in this case, so p1, the difference, okay, we'll just add them up, p1 v and delta v, and p2 delta v, but it will be negative sign again. For this work done, we are considering not the work done on the fluid, but the work done by the fluid, but the work done on the fluid, so we have to take negative sign here. This is the main thing, I think this has to be understood well. Okay, I've given one example, just think about it. This is the only case of external work and burden on the fluid, on by the fluid. Okay, part of this work, though this is a net work done on the fluid. Okay, part of this work goes into changing the kinetic energy of the fluid, and part goes into changing the gravitational potential energy. Okay, this work done, what will be the work done? Energy will be used up, it will be used in changing the kinetic energy and also the potential energy, because you have to rise some height, the height changes, so some work has to be done on changing its height. Okay, energy has to be spent, and some will be used up in increasing the velocity, that is a change in kinetic energy. Now the later part is quite easy. The density of the fluid is, we'll just write mass in terms of density and volume. What is mass? Mass is density times the volume, and volume we have written earlier, a1 v1 delta t. So this is the volume, this is how we write the density. Okay, so how much will be the mass? This will be rho times delta v. Okay, and is the mass passing through the pipe in delta t. This much mass of the fluid will be passing in delta time rho delta v. Then change in gravitational potential is this. Okay, the potential energy here and here. Okay, the density is same, the volume here was delta v, the volume here was rho delta v. Okay, the volume is same, but the difference was in the how we have written the volume, that was rho, here it was what, a1 v1 delta t, and here it was rho a2 v2 delta t. Okay, and now this was the mass, and what is the formula of potential energy? Mgh. So mass we have written rho, we don't write the whole thing, rho delta v gh1 here, and rho delta v gh2 here. So difference we can calculate, this height is more, the potential will be more here, and we can find the difference here. Okay, so that's what we have done, we have just taken the difference here. Okay, similarly for kinetic energy, the okay, velocity will be different. What is kinetic energy? Half mv square, and mass we have written as delta rho delta v. okay, half rho delta v, the difference of the square of the two velocity v2 square minus v1 square. Now we can employ work energy theorem of chapter 6, that is the work done is equal to change in kinetic energy. Okay, so work done was the work done by the external force. Okay, what, and we can elaborate the work energy of work done by the external force plus work done by conservative force is equal to change in kinetic energy. What is the work done by the conservative force? This is nothing but delta u, change in potential, negative or change in potential energy. And when we send this delta u on the right hand side, the work done by the external force will be delta k plus delta u. Okay, work done by external force we have calculated, that was p1 minus p2 delta v. This change in potential energy was, this is the change in potential energy we have. Okay, just a second, this was a potential energy, we will write this down, and change in kinetic we will write this down. Okay, and now we will just divide it by delta v. So what we will left with will be p1 minus p1 is equal to half rho v2 square minus v1 square plus rho g h2 minus h1. So this is, and when we rearrange it, okay, we'll just take the p1 and half rho v1 square on this side, and okay, and rho g h1 on this side. So what we'll get on just rearranging them, p1 plus half rho v1 square plus rho g h1 is equal to p2 half rho v2 square plus rho g h2. Okay, this is the equation, Bernoulli's equation we have obtained. It's just simply said, because it is been divided by volume, so pressure energy per unit volume plus, because it, half mv square divided by volume, that is rho. Okay, so kinetic energy divide per unit volume plus uh, potential energy per unit volume is a constant. Okay, is a constant, very important theorem. We will prove a lot of application are there, we'll discuss that. Okay, yeah. In words, the Bernoulli's relation may be stated as follows: as we move along the streamline, the sum of the pressure, kinetic energy per unit volume, and the potential energy per unit volume remains a constant. Note the up, and then as I told you, we have some assumption that we have made for Bernoulli's principle to prove it, and we have to look at the assumption too. Note that in applying the energy conservation principle, there is an assumption that no energy is lost to friction. Obviously, in practical case, it will lost. So this is for an ideal case. There is no friction we are assuming. But in fact, when fluids flow, some energy does get lost due to internal friction. This arises to the fact that in a fluid flow, the different layers of the fluid flow with different velocities. These layers exert frictional forces on each other, resulting in a loss of energy. This is termed as a viscosity. Okay, so in the fluid, we'll discuss in the later part of the chapter. The fluid is, there are some different layers, and these layers, they have different velocity, relative velocity to each other. The upper layer will be at the highest velocity, the lower layer will be zero velocity. So there will be a constant velocity, different velocity gradient will be there, and because of that there will be repulsion. Okay, there will be friction, and that is called viscosity. So energy will be lost in the form of heat due to viscosity. And yeah, the lost kinetic energy of the fluid gets converted into heat energy. Thus Bernoulli's equation ideally applies to fluid with zero viscosity or non-viscous fluid. Only we can take in ideal case. Okay, another restriction on application of Bernoulli's theorem is that fluid must be incompressible. Yes, the elastic energy of the fluid is also not taken into consideration. Okay, if it is not incompressible, compressible, then some part will be, some energy will be used up in compressing it. Okay, so that we are not taken in consideration. And obvious, but the fluid is like water, the compressibility is very less. Okay, that can be ignored even in practical cases. It has a large number of useful applications and can help application of wide variety of phenomena for low viscosity incompressible fluid. Okay, as I told you that it is applicable for truly applicable for uh, incompressible fluid. Okay, so it can be applied to low viscosity incompressible fluid. Bernoulli's equation also does not hold for non-steady or turbulent flow. Okay, we have to keep in mind that it can only be applied to streamlined or laminar flow, because in that situation velocity and pressure are constantly fluctuating in time. Okay, so so that it can be only applied to steady flow or laminar flow. When a fluid is at rest, this velocity is zero everywhere. Bernoulli equation becomes, okay. This is also important result. Okay, if it is in rest, what will happen? Velocity will be zero. So we will only talk about pressure, energy, and potential energy per unit volume. So P1 rho GH1 plus is equal to P2 plus rho GH2. P1 minus P2 gives this much. Okay. So now we will talk about the Torricelli law in the next video. I hope you like this video. There's, okay. Let me know in the comment section what feedback you want to give, and like, share, and subscribe to this channel. Thanks for watching.